Hello and welcome back. My name is Mr. Dean Kovalt, and today we are going to talk about reliability or uncertainty and measurements. So, one of the biggest things and the biggest struggles that students have is with significant figures. So, here I'm going to talk about where those significant figures come from and why they're so important. They have to do with the precision of the instrument that you're using. So the less precise your instrument, the less significant figures you have. The more precise, the more significant figures you're going to have. So I have a few things here that I want to talk about pretty quickly. So here you have a data table, and in the data table you have the year, and I have two sets of concentration values or measures. So this is the concentration of carbon monoxide. Both of these are the same concentrations of carbon monoxide. The data is pretty much the same, except the data here is reported to one decimal place, and here it's reported to just the ones place. So what this means is that when they are reporting data like this, depending on what instrument they used, you either get more precise or less precise data. And you can only report the number of digits that your instrument allows you to report. Now, the rule of thumb, or I shouldn't say the rule of thumb, but the rule is that when you are reporting data or your measurements, you report with all these certain digits, the digits that you are sure about, the certain digits, plus one extra digit that's estimated. So the last digit is always going to be the estimated digit in any reported value, in any reported measurement. Okay. So for example, if we look here, this reported value, if we look at 6.9, again, this is ppm, parts per million. So what this is telling me is that for 1993, the CO, or carbon monoxide concentration in parts per million, was 6.9. So if we are reporting our values with all certain digits except for the last one is the estimated digit, then that's telling me that this 9 is estimated. So there's wiggle room in that last digit. And we assume, unless we are told otherwise, we assume that it's either plus or minus 1 of that digit, or whatever the place the digit is in. So the way we report this is, so it would be 6.9, and since the 9 is in the tenths place, then it's going to be plus or minus 0.1. So plus or minus 0.1. So what that means is that the value can fluctuate between 6.8. So it could be, if I subtract 0.1, it would be 6.8, right? So 6.8. Or if I add 0.1, it would be 7.0. So that's what the plus or minus 0.1 is telling me, right? So that I get that from the fact that the last digit is in the tenths place, 0.9. And that's the same thing for all of these that have 0.5 or 0.1 that have a digit. Their last digit is in the tenths place, so that means it's plus or minus 1 in that place, right? So this is accurate to or precise to the tenths place, 1 decimal place. Here we don't have any decimal places, so this is less precise. So this is only 1 digit, so that is the last digit. So the last digit is the estimated digit. So this is telling me that the reported value, if this is going to be 7, and it's going to be plus or minus 1, so plus or minus 1. So there's a larger range of error in this measure because it's in the 10th place. So basically, if I add 1, that means the range would be 8 being the highest and 6 being the lowest, right? So, and this is ppms, right? Here the range is much narrower because the precision is better. So the wiggle room is still plus or minus 1 in the last digit. So in this case it's 0.1. So the wiggle room here is much smaller. So I get a wiggle room of 0.2. Okay. So that's how we report the values and the measurements, is we report them with all the certain digits that we know for sure, plus 1 estimated digit, and that estimated digit is always the last digit. So if I get a measure like here, if they're presenting this measurements in a table, then the last digit is assumed to be plus or minus 1, unless they say otherwise. It could be plus or minus 2 or plus or minus 5. It depends on what they tell me. If they don't tell me anything, then I assume it's plus or minus 1. So where do these digits come from? They come from measurements. So if I go through this quickly, so here's an example of a ruler that I have. I drew on the board. So here's a line. Maybe this is the edge of a table. Maybe this is the length of a piece of paper. Whatever it is, I am measuring. I am using my tool. So how do I figure out what each of these lines mean? So I have to know what each line means so I know what I can estimate to. So the way you do that is you take 2 consecutive numbers, so this would be 0. But you take any 2 consecutive numbers on your measuring device, and you count the number of spaces or increments in between. So I have 1 to 2, so I subtract 1 from 2. So what I'm going to do is the number that's between here, I subtract the higher from the lower, so 2 minus 1 centimeters. And then what I'm going to do is I'm going to divide that difference by the number of increments, or the number of spaces that I have. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to divide that by 10. So this difference is 1. So 1 centimeter divided by 10 gives me 0.1 centimeters. So that tells me that each line on here represents 0.1 centimeters difference, or 0.1 centimeters difference. Or so if I start at this line here, 0, this line is 0.1, and then 0.2, 0.3, 0.4, and then I have 0.5, 0.6, 0.7, 0.8, 0.9, and then 1. And then so anything in here is going to be 0.1 after the 1. So 1.1, 1.2, 1.3, and so on. So now that I know that each line represents a tenth of a centimeter, then that is going to tell me my certain digits. That's going to give me certitude about what digits or certain digits I can measure. So any line gives me certitude. So if what I'm measuring goes past a certain line, I know for a fact that that is part of my measurement. That's going to be a certain digit. So for example, here I'm measuring my line. I have 1, 2, so it's definitely 2 centimeters at least. And now I can use my lines here to add. So 2.1, 0.2, 0.3, 0.4, 0.5, 0.6, and 0.7. So it's definitely past this line. So I know it's definitely 0.7. So it's 2.7. So those are going to be certain digits that I know for sure. So for 2.7 centimeters is what I know for sure. Now those are certain, but I get to estimate one more digit. So what I do is I mentally divide this up into 10 spaces and I try to estimate where it is in the line. So it looks to me like it's in the middle, so I might say 5, right? So if I divide this space, this is 1/10 of a centimeter. If I divide this in 10, then that's going to allow me to go to the hundredths place. So I'm dividing the tenths place into 100 into tens, and so that allows me to estimate one more decimal place over. So if it's in the middle, then I might say, oh, this is 5. So this last digit I estimated. That 5 is an estimate. Someone else could say, okay, maybe it's a 4, or someone else could say, oh, it's a 6, right? It's an estimate. So there's wiggle room in here. So then this would be all I'm allowed to report. I'm not allowed to report anything else except what I am certain of, and the last digit is my estimate. And I stop there. I'm not allowed to go anywhere else. And so then if I report this, then the way I report it is going to be 2.75, right? And then there's wiggle room in here, plus or minus 1. So it's going to be plus or minus. And then now it's plus or minus 1 in the last digit. If the last digit is now in the hundredths place, then it's going to be 0.01. So that's the way I would report that. Okay. Now, sometimes you can't estimate to the last digit, and then sometimes, and that has to do with the instrument you're using. So over here, sometimes your graduated cylinders will have divisions of 10 between the numbers. Sometimes they're divisions of 5. What do we do when there's divisions of 5? So really quickly, I have to figure out what each increment means. So I do the same thing I did over here. So I take these two numbers and I say, okay, so 5 minus 4, and this is in milliliters. And then I'm going to divide by the number of increments I have between the numbers. 1, 2, 3, 4, 5. So I divide by 5, and that is 1. So 1 milliliter divided by 5, that gives me 0.2 milliliters. Okay, so that tells me that each of these lines is 0.2 milliliters. So now when I have, let's say my meniscus, if I have a meniscus, let's say this is my meniscus, okay? So here, the meniscus, the bottom of the meniscus is maybe here, right? Not quite in the middle, maybe a little bit higher, right? So how would I report this? Normally, we want to estimate to the next decimal place over by imagining that we're able to divide the increment by 10. But in this way, we can't, because watch what happens. So I have 5. So this is going to be 4.2, right? This is 0.2, 4.4, 4.6, and then up here we have 4.8, right? Increments of 0.2. But look at here. What's between 0.6 and 0.8? 0.7, right? So 0.7, there's no line for 0.7, so I have to estimate 0.7. So I'm only allowed one estimation, so that's it. So I don't get to go to the next decimal place for this. I'm only allowed, if I'm between the lines here, 0.7 is what I'm estimating, and that's all I'm allowed. Okay? So thank you very much. I hope that was